Hello everyone, welcome to another video. In this video, let's take a look at the bipolar junction transistor, the BJT. And it says, let me go ahead and select the pen right here. And it says, transistor is short for transfer resistor, a term which provides something of a clue as to how the device operates. The current flowing in the output circuit is determined by the current flowing in the input circuit. Since transistors are three-terminal devices, one electrode must remain common to both the input and the output. So if you look at the transistor looks something like this. All right. So what it means that one electrode must be common to both the input and the output. This is the base, this is the collector, this is the emitter. The input is the base. In a common emitter configuration, the emitter in this case is common to both the input and the output. The output is taken from the collector. All right. So let's continue reading. Transistor falls into two main categories: bipolar junction transistor (BJT) and field effect transistor (FET), and are also classified according to the semiconductor material employed, silicon or germanium, and to their field of operation, e.g. general purpose, switching and high frequency, etc., etc. Various classes of transistors are available according to their applications. Scroll down. BJT operation. Bipolar junction transistors generally comprise of an NPN or a PNP junction of either silicon or germanium material. Figures 5.17 and 5.18. The junctions are in fact produced in a single slice of silicon by diffusing impurities through a photographically reduced mask. That is how transistors are built. We're not going to get too concerned about that, but let's take a look at the image. So that is basically what they're talking about. You have three type of material. You have each material is either an N or a P type material. In this case, we have an NPN transistor. This one here is an NPN transistor. I go ahead and select the pen. This here is an NPN transistor. Why? Because in this case, the collector, which is this terminal here, is of type N. The base is of type P, and the emitter is of type N. So it is an NPN transistor. And in this case, we have a PNP transistor, which the collector is P, the base is N, and the emitter is of type P. All right, so let's continue reading. It says figure point 19 and figure point 19b respectively show a simplified representation of an NPN and a PNP transistor together with their circuit symbol. In either case, the electrodes are labeled collector, base, and emitter. And note that each junction, I'm reading from right here, it says note that each junction within the transistor, whether it be collector base or base emitter, constitutes a PN junction. Figures 5.20 and 5.20b respectively show the normal bias voltage applied to a NPN or a PNP transistor. This is very important when understanding transistors. Let's go ahead and take a look at the figures. This is what they're talking about. Figures. These are figures. Yes, 5. Yes, 5.19. So notice that this here is the collector base emitter junction. Each junction constitutes a NPN or a PN junction. The base emitter is a PN junction, and the collector base is also an NP junction. So here you can see the electronic symbol for the NPN transistor. Why is an NPN transistor? Because notice the arrow on the emitter, the arrow is pointing to the direction that current is flowing. When you're dealing with an NPN transistor, which is in this symbol right here, the arrow on the emitter is pointing to the outside, meaning that the current is going to flow from the collector to the emitter. All right, so now let's compare that with the PNP, which is this one here. Notice the direction of the arrow on the emitter. This is the flow occurring now is it from the emitter to the collector, all right? In this case, the base is a p-type material, okay? And in this case, the base is an n-type material. That also is very important because if we take a look at this figure now, this is the bias of the transistor. In order for the transistor to work, it needs to be biased. And in order to bias the transistor this is an NPN. Let me go ahead and this is an NPN transistor. Why is an NPN transistor? Take a look at the arrow on the emitter. The arrow on the emitter is pointing to the outside. So that means that the emitter is N, the base is P, and the collector is N. In the NPN transistor, the base is positive. So the BVE, take a look at this parameter here. BVE is the voltage base emitter. The voltage base emitter the base needs to be positive in relation to the emitter in order for the transistor to be biased and start conducting electricity. All right, and notice the bias for the collector. The collector is more positive than the base. This junction here, the collector base junction, is reverse bias. But the important part here is this BVE, which is the bias of the base in relation to the emitter. Okay, that is very important. And then on the NPN, on the PNP, is the reverse. Notice the arrow of the emitter is pointing to the inside. So now current flow is in the other direction. So the base in this situation is of N-type material. So the base now, BVE, take a look at BVE. So now we need to make the base negative in relation to the emitter. That is important. All right, so let's take a look now. Let's take a look now at current gain. It says, the current gain offered by a transistor is a measure of its effectiveness as an amplifying device. The most commonly quoted parameter is that which relates to a common emitter mode. In this mode, the input current is applied to the base and the output current appears in the collector. The emitter is effectively common to both the input and the output. The common emitter current gain is given by this formula here, which is HFE. The HFE is also the gain, which is the hybrid parameter. Let's continue reading here. It says, I'm right here. Let me select this again. I'm right here. It says where the HFE is the hybrid parameter, which represent large signals in DC forward current gain. IC is the collector current. IB is the base current. When it's one thing that I forgot to mention is this part right here, which relates to this formula. It says to put this into context, the current flowing in the emitter circuit is typically 100 times greater than that flowing in the base. The direction of the conventional current flow is from emitter to collector in the case of a PNP transistor and collector to the emitter in case of an NPN device. The equation that relates to current flow in this collector base emitter current is equals to the current on the emitter is equals to the current of the base plus current of the collector. And they talking about the fact that in the so we have two exercises here. We're going to use this circuit as reference. This is a NPN, actually yes, an NPN transistor in the common emitter configuration. Notice that the emitter is common to both the input, which is in the base, and the output, which is the collector. And it says a transistor operates with IC collector current 30 milliamps and IB base current 60 microamps. Determine the value of IE and HFE. IE is the emitter current and HFE is the gain, the hybrid parameter. So if we remember the formula that we saw, we know that IE, so IE is equals to IB plus IC. All right, so IE, which is the emitter current, is equals to the current flowing in the base plus the current flowing in the collector. We have the collector current and the base current. So this is equals to 0.6 milliamps plus 30 milliamps. What I did, I converted this base current from microamps to milliamps. So 600 microamps is equals to 0.6 milliamps, right? I just moved the comma 3 places to the left. So this is equals to 30.6 milliamp, right? So that is the current flowing through the emitter. The next thing that we need to do, we need to calculate the HFE or the gain. So the HFE is equals to the collector current over the base current. So we have the collector current, which is 30 milliamps. That's 30 times 10 to the minus 3 over 0.6 times 10 to the minus 3. And let's pull the calculator. So that is 30 over 0.6, and that is equals to 50. So the HFE is 50. So let's do the other one. It says a transistor operates with a collector current of 97 milliamps and an emitter current of 98 milliamps. Determine the value of the base current and common emitter gain. Again, we're working with the common emitter configuration. In this case, we have a collector current of 97 milliamps and a base current, no, actually an emitter current of 98 milliamps. And we need to calculate the base current. So this is the formula. Current of the emitter is equals current on the base plus current of the collector. But now here we have the emitter current. We need to calculate current in the base. So current of the base is equals to current of the collector minus, actually it should be the other way around. Is equals to current of the emitter minus current of the collector, which is equals to 98 minus 97 equals to 1 milliamp. All right, so we have 1 milliamp flowing into the base. Notice that the smallest of the current is the current of the base, and then the output, which is the collector, is 97 milliamps, and the emitter is the sum of both of those currents. All right, so the next thing is to calculate the current gain, or the HFE. By the way, in some books you find HFE, and in other books you find beta, which is this symbol here. Same thing. Is equals to collector current over base current. So that will be 97 over 1, which is equals to 97. That is the HFE, or the gain of the transistor. All right, so thanks for watching, and see you in the next video.